The implicit unsteady model is the only unsteady model available with the segregated flow and the segregated fluid energy models. It uses the implicit unsteady solver. The implicit unsteady solver becomes active when the implicit unsteady model is active. Its primary function is to control the update at each physical time for the calculation. It also controls the time step size. Slide 43. The explicit unsteady model is available only with the coupled energy model. It is only compatible with the inviscid and laminar viscous regime models. It uses the explicit unsteady solver. The explicit approach is the alternative to the implicit unsteady model. The explicit unsteady solver becomes active when the explicit unsteady model is active. Its primary function is to control the iterative update for the calculation. A model with unsteady terms such as the coupled flow model or the segregated flow model must first be activated to expose the time model selections. Before or after selecting the equation of state model and the viscous regime, select the relevant time model radio button. The explicit unsteady model is only compatible with the inviscid and laminar viscous regime models. The model selection dialog shows the time model activated. To set the time step for implicit unsteady simulations, select the implicit unsteady solver under the solvers node. The physical time step can be set using the time step property in Properties window. In addition to a constant, you can enter an expression directly. Well, the main question out of this discussion is how to decide whether to go for the steady or the unsteady model. The answer many times is simple, but sometimes can be tricky to decide. In most situations, the physics being simulated indicates the choice between the steady and unsteady or implicit and explicit models. Some simulations are time dependent, hence the choice of unsteady model is obvious. Examples of such situations are time varying boundary conditions, sliding or deforming mesh problems, free surface, that is VOF problems, and transient heat transfer. In some situations, however, unsteadiness in the physical problem is not readily apparent. This can be seen when there is failure to converge when running with the steady model. One example is the solution of flow past a cylinder. At certain Reynolds numbers, the flow is unsteady because of vortex shedding, and it is incorrect to use a steady solution approach. When physical instabilities do exist, the correct way to model them is to perform a time-dependent simulation. We need to choose an appropriate time step. This is based on representative straw-hole number. If the transient problem that we are modeling is periodic in nature, we may have to use accumulated time average statistics. Using the steady model for unsteady physical phenomena is not recommended. Running an unsteady problem with a steady model is equivalent to using an inaccurate time step in an unsteady simulation. The next decision that we need to make during an unsteady simulation is to decide the time step value. The choice of time step is an engineering judgment. This is similar to the decision on grid refinement. We need to understand the timescales of the physical phenomena. The convective timescale CFL is important in cases where we are tracking the convective dispersion of scalar through the flow. If molecular diffusion is dominant, we consider the von Neumann number. For large eddy simulation LES, we consider the turbulent timescale. For modeling vortex shedding, we consider the Strawhall number. In engineering, motion can be defined as the change in location of a body relative to a particular frame of reference. Such motion is imparted to any fluid in contact with the surfaces of the body. This must be considered in an analysis of the fluid behavior. Some examples of motion-induced flows are situations like mixing vessels, where mixer blades drive the flow. Other examples are turbo machinery, flexible diaphragms in medical applications, ship and propeller motion. Next complex modeling problem is the one which involves fluid structure interaction. In star CCM+, it is also possible to model the motion of rigid bodies in 6 degrees of freedom with the fluid system. Modeling motion is not part of this course, and hence we will not go into more detail. We will only see some introductory concepts. There are 3 broad categories for defining motion in star CCM+. The first category contains those methods that involve actual displacement of mesh vertices in real time. We can use these methods with a transient analysis. The second category contains the method where an unsteady motion problem is converted to a steady state problem. This is done by imposing a moving frame of reference on a static mesh. Rigid rotation and translation can be simulated in this way. The third type of motion is a corollary of the real-time displacement. This applies only to harmonic balance flutter. CFD is about virtually simulating fluid flow and heat transfer. When we say we are modeling fluid flow or solid conduction, in reality, these fluids and solids are materials. Hence, in a simulation also, we have to provide or model material behavior. Some simulations that we perform in star CCM+ involve modeling a substance such as air, water or aluminium. Others involve several substances such as combusting mixture of gases or a sloshing mixture of air and water. The material model handles the definition of these substances. So, the question arises, why do we need material models? The material model is responsible for managing the material. These materials are substances being simulated in the continuum. The material model manages various thermodynamic and transport properties relevant to that material. It also takes care of the transport properties relevant to the physical processes being modeled in the continuum. There are 3 general types of material models available in star CCM+: single component, multi-component, and multi-phase mixture. Each of these material models will manage one specific type of material. The single component model deals with a pure substance. The multi-component model manages a multi-component mixture. The multi-phase mixture model manages a multi-phase mixture.